then define talk about this Schlaefli integral, another representation of the Bessel function. So, so that is this representative equation 14.37. So that's another way to express the Bessel function. So for some reason, your textbook changes the F, which is not quite sure what it is, but I mean, it's basically it's a Bessel function. 14.37. We try to talk a little bit more about that. You know, your textbook called F, but it's actually a J. It's a contour integral. The contour can be a closed contour or going around a branch point. It depends on whether nu is an integer or not. X over t minus 1 over t plus 1. Okay. So you recognize the numerator is in the integram is just the generating function of the integer order of all the j sub n, right? And then you divide it by this t to the nu plus 1 power. And so I think we did that integer order, but we can we can we can do it again and then check that indeed will give you the Bessel function for integer order. So the contour is around a branch point. If nu is a non-integer, then obviously you have a branch point at t equals 0. This is the t plane. Right. If nu is an integer, then it depends on what integer. If this is in the numerator, it's at least t or t to the power positive power of t, then there's a pole at the origin, obviously, and there's no branch point for integer, and but c is defined as going around the branch point, so going around doesn't matter. You can write a little circle around a branch point, but it actually doesn't matter because you can always deform it. Right? And then the beginning and the end is at t goes to negative infinity. But it's just going around the branch cut for non-integer nu. So going around like that. Right. And now the first case is going back to nu is integer. Then the branch cut, you don't have the branch cuts, and actually because both are from negative infinity to negative infinity, and there's no branch cut, you can always connect the two together, and then you actually don't need to worry about the asymptotic behavior of the integram at t equals to negative infinity, because when you close it, it doesn't matter how you close it, because the only pole is at t at t goes to 0, right? Actually, it's always a pole. Actually, this is not even a thing, a finite order pole. This is actually it's essential singularity, because you remember there's a 1 over t in the exponential function that make it essential singularity. But that doesn't matter. We can still evaluate that. For nu equals to n equals to integer, then we a sub n is just I think we did that last time. But, now this is now a closed curve, closed circle around the origin, the essential singularity, but in a positive sense, right? And so it's the same integram. But then now we can use the generating function for this the numerator. And now because we already use m, we use n, then we use m as minus infinity to infinity. There is m of x e to the power m and dt. Right. Then the only factor depends on t is this one over t to the nu plus 1 and t to the m power. So altogether t to the m minus nu minus 1. And last time I think we already figured that out. So that is that singularity is give you the residue. So first you have multiplied by 2 pi I, so you cancel the 2 pi I. So the residue of this factor is, or you can, it's not even a factor residue. You can, let me call it residue, but it's just the power of t. So you just integrate it, the usual compact integration. The only non-zero value is when m equals to nu, right? There's a delta m nu, because you need until to the minus 1 power here. And I think we argued that last time. So this changed to a cancel this one. So you sum over m is m. The integral of t is just basically delta mn. The conical delta, and you get the 2 pi, cancel the 2 pi I. That is g. So using that, just check that this is just g. Okay, so that you can see that, right? So I think we argued that last time, so I don't want to go through that again. But you know that this is just a loop integration of a function which is t to a certain power. So you only is non-zero if the integram is 1 over t, right? Only the 1 over t term will give you finite result, and all the other terms are 0. So we check that. So this integral form works for integer nu, but what now for non-integer nu, we argue that this also expressed the solution of the Bessel equation. So we call it the Bessel function for all the nu in this case. Okay, and yeah, different way to argue that. And one way to do it is just let the differential equation operate on this integral and see what happens. And the differential equation is the first equation in the chapter. I think but we just give it a name for that. So the equation is operator on J mu x, which is defined as this x squared d squared dx squared plus x dx plus x squared minus nu squared. So this is the operator L, and operator on J sub mu is 0. Okay, so that's the Bessel equation, writing in L in the operator form. Now we want to, so this J is the solution, but we want to check whether this is a solution. So we park that in here. So let L J nu now equals to, substitute this into the integral. And this is an operator on x. The integral is on t, so we just operate in the integral. Right. And that it actually doesn't depend on t, so you can write the t out. U plus 1 operate on this generating function. All right, and from this we can either just explicitly operate on this taking this derivative on this function, and then transform the function to the form of in the textbook, and which is I think it's a homework problem somewhere later when we talk about a Hankel function. So I think I assigned that as a homework. So, the find is in the textbook. Yeah. Equation 14.38. So you want to just writing it like that. This operate on this using this operator after some algebra. It's actually quite a lot of algebra. You can convince yourself that actually this I missed the DDT first. The whole thing is in a derivative of t ddt. Then the same exponential function and divided by t nu plus 1. Just t nu, there's no plus 1. Then nu plus x over 2 t over t plus this is a plus. Okay. From here to there, there's just operate on that and then checking term by term and just work out that exercise. Right. And the one way to do it is like that. Yeah, there's another way to do it that which I posted a video on YouTube video on about how to do that. Just operate on the generating function and using the property of the generating function form, and show that it recovered this form also. So either way, you get to this. I won't go over that. So either way, is taking time to the operate on generating function is slightly easier and slightly shorter. If you do a derivative by derivative of this function, and then group everything so that you convince that taking the derivative of x on here on this function is the same as taking the t derivative on this whole thing, and convince yourself they are the same, then that's a choice. I mean, there's a proof of this, right? And that take maybe 20 minutes to do that. Okay. But anyways, we just want to discuss the reason we do that and why this will give you 0. And because we want to show that this operator that will give you 0 on the right-hand side. Right, and because you write it in the ddt total derivative, then you are starting at negative infinity to going around and going to negative infinity again. So after you write in this form, so basically this integral is just whatever this curly bracket and evaluate at the end point minus the initial point. And both are at t goes to infinity, only the difference is the phase, which in this argument doesn't matter. And the argument is like just very simple. this is consider x is positive, because this is for x is positive, right? Then we define this as x is for positive x, which is usually we define for this Bessel function. So if you want to calculate the Bessel function for negative x, of course you can do that using some symmetric property of Bessel function, or another way is basically now you just flip this contour around. Instead of ending at negative infinity, then you end in a positive infinity, which is fine. You can still define that, right? And now for negative, for x is positive, so the endpoint, now you evaluate endpoint, we just subtract the endpoint minus the initial point, but at both ends, you have evaluate t at negative infinity. So you evaluate everything, and the largest factor is the controlling the whole magnitude is the exponential function, and that's the two terms. For 1 over t, obviously, if t is going to infinity, this 1 over t is going to 0, so that doesn't matter for the exponential function. So that's exponential 0 is just give you 1. So this term, you have t is negative infinity, and then multiplied by x, which is positive. So exponential of negative infinity, basically, and that will give you 0. And there are other factors in t. So there's t here, there's t here, right? This will give you infinity, but this is just linear in t. This is exponentially growing, exponentially 0. This is just linear growing in t, and depends on this new whether it's positive or negative, that can be large or small. But then even if this 1 over t becomes large as large t, and the exponential function still make it 0, because it's exponentially small, right? So once you're writing it as a total derivative and with this factor, then this is 0. You can argue that. It's okay. So this is the whole argument. It's okay. So the main task, or the most involving task in showing this is to show that L operates on that with this L defined like that can be written as this form, which I'm not showing it right now, but you work on that in the homework. It's okay. So, but the idea is that once it's in the total derivative, then you can show that this satisfies the Bessel equation in this way. The L operator on J would be 0. Okay, so that is show that it satisfies the Bessel equation. That's the textbook talk about another argument that this function give you the correct asymptotic behavior at actually the correct small x expansion as the series. So because we already said that J sub nu can be represented by the series expansion in 14.6. 14.6. So basically 14.6. You can look at 14.6 at the x goes to 0 limit, and this J sub nu x tend to, when x is 0, and for non-integer nu, then you pick up just the s equals 0 term. So -1 to 0 is 1, s factorial, 0 factorial is 1. It goes to a gamma nu plus 1. And then just keep the first term, x over 2 to the nu plus 2s, s is 0. It should tend to something like that. Okay. Then So that's from the series solution, and you can also show that this expression will also give you this expression for small x. So that is also you can show that, and I mean it's not difficult to show that, but we don't need to go over it. I mean, it involving the gamma function. Also, this gamma function is also defined by a contour integral around a branch point. So finally, you show that for a small x is reduced to a gamma function that depends on this this kind of integral. And, you just once you use that, you can convince yourself this is true. And so this definition will give you the correct form as compared with the series solution. So the two are the same, and which is reasonable because as nu goes to integer, you recover the j sub n, and likewise this series solution, as nu goes to integer, you also recover j sub n. So both will recover j sub n. And although you can argue that although the two limit is the same, they might not be the same for non-integer nu, but it turns out to be the same, right? So this is the right integral representation. So we'll take that, and then from here it looks like it's just another integral representation, and but what we'll use it later is when we talk about the Hankel function, in particular the asymptotic behavior of this Hankel function. And actually, the Hankel function actually there are two ways to define this Hankel function, but the contour representation of the Hankel function will use the contour like that to define the contour in the Hankel function, because the Hankel function is not defined by the whole loop of the integral whole. What this contour C is partial. It actually goes part of that. So basically, the whole contour is separate into two. So there's an addition of the two Hankel function this way. But we'll talk about that later. Okay.